Okay, so welcome everyone. So this will be Joseph's thesis defense. And just to give the logistics of it, Joseph will give a talk for about an hour, and we'll have audience questions. Then we go to a closed session with the committee where we ask questions. The committee members are Eugene, who's online, and Pulkit, who's here in person. And assuming everything goes well, then we will have a celebration at probably around 6:30. And why don't we do that in the same, in here, come back to this location at 6:30. I know some of you will go home, but hopefully you can stick around. Okay, so yeah, it's been really great having Joseph in the lab. You've definitely done one of the most unusual and unique PhDs I think I've seen in my time here. So it's been unusual in a few ways. So one is that most PhD students, I think, come in, they don't quite know what they want to do, they pivot around, they have a few years of angst, and then finally they find their topic. But Joseph knew exactly what he wanted to do from the very start. I think that your first version of your Neural MMO project, which is what the thesis is about, was high school? Was it high school or
it depends which one you want to count, but technically yes.
But it was very early on, and I got to know Joseph when he sent a proposal, when I was at OpenAI. He sent a proposal, application proposal, with a kind of very detailed write-up of how he would make a multi-agent simulation that would lead to all kinds of emergent intelligence and then solve AGI. And it was so exciting, and we had to get him, and I had to take him then as my PhD student too. And you basically stuck to that plan. And it's not done. I think it's a career level ambition, but there's a lot of progress, which you'll see in just a minute. So yeah, Joseph has really done things that are innovative and unique, in my opinion. Sometimes it's been an uphill battle because your approaches haven't always been the standards of the field. They haven't been like these, fancy NeurIPS algorithms or whatever it is. It's been more about the data, the environments, the tooling, the platforms, the community. And I think that is just another sign of innovation, really. So yeah, it's been great having you in lab. Your passion for games has been very inspiring. I think one of the memories that I have, which I really appreciated, was when you set up the Minecraft server for our group during COVID, and we had lab meetings and our socials in the Minecraft server. But I know that you say that Minecraft is a terrible environment for agents, and so instead you have your own environment, and that's what we'll hear about next. So let's go for Joseph's talk.
Thank you for the introduction, Philip. As you alluded, this has been a project I've been working on for a very long time. I'd like to start with a little bit of background that led me to where I am now. And as Philip mentioned, there are no fancy algorithms, there is no math. There will still be an hour of content. Reinforcement learning is a specific set of processes for learning through interaction with an environment. The agent is parameterized by a neural network, and the environment is usually a game, a simulator, or perhaps a robot. I've chosen this graphic for the environment because a lot of research is done on Atari. This was true 8 years ago, and it is still true today. Now, I couldn't help but make the rather obvious observation when I started that Atari really doesn't look much like the real world. So ideally, we could train something in a more rich setting. And I find it odd, and I found it odd at the time, that there wasn't that much interest in looking for new environments, better sources of data for reinforcement learning. And I found that odd because in the rest of AI, it's all about the data. Quality of data, size of data, this is recognized as important. Now, this is simplifying a little bit because it's a bit harder in reinforcement learning. We can't really train agents directly in the real world. We could attempt to flood the world with robots, but that would produce so much data and be so expensive. Perhaps with $7 trillion we could do this, but I think we might run out of money. So barring training in the real world, the key fundamental questions of my work are, what is the right environment for training generally capable agents? And more importantly, how do we build that environment? Those are hard questions. So let's answer some easier ones. Whatever we build, we definitely want something that is going to be computationally efficient and interpretable, but lots of things fit that bill. We'd like to say something that's realistic, but realistic and computationally efficient don't mix too well. So instead, we'll say cognitively realistic. We want something that poses the same types of high-level reasoning challenges as are found in the real world. There's a very long list of those, but in my mind, some of the ones that stick out are that the real world has lots of people, lots of agents, requires mixed cooperation and competition. It requires short, medium, and long-term decision-making. And then the world itself is also a key driver of complexity. There are economic forces of supply and demand. There are incentives to specialize to specific jobs or roles. And there's a lot more than that as well. But if we could just capture a handful of these properties in an efficient simulator that we could use, that would be enough to power a whole new wave of progress in reinforcement learning. Well, I just described an MMO, a massively multiplayer online game. This is a genre that ran cities of players on 90s hardware. The games industry spent decades perfecting the art of creating interesting high-level gameplay with all of those properties I just described, but very efficient underlying dynamics. It can look the same as another game on the surface, but be 100, 1,000 times faster under the hood. Really, this was just the perfect storm for AI. I'll give you a couple quick examples. You can have two players on completely opposite sides of the world that never see each other, doing completely different things, that still have a large influence on each other's behavior by virtue of the economy. You can also see incentives in these games to replicate social structures that are present and important in the real world. For instance, there can be highly rewarding content that requires many players to complete and is difficult. You have to learn it. So once you learn to do that content, it is in your best interest to teach some other players how to do it with you so that you can get those rewards. Neural MMO is a massively multi-agent environment for reinforcement learning research inspired by MMOs and borrowing some of the simulation techniques from that game genre and from the industry. Now, it's not going to be anywhere near the complexity of the real world. It's not even going to be near the complexity of a full-scale MMO, but it is going to be much more complex than most reinforcement learning simulators that we have available, and you're going to be able to run it and train it on one GPU. When I started this project way back then, there weren't that many good environments out there for reinforcement learning. Really, the most notable one was Atari. Yeah, there were some control environments, but we're not going to consider those for the purposes of this. Now, over the next several years, many environments were developed and released, but many of the most complex and interesting ones were these large-scale OpenAI and DeepMind projects, where I found the manuscripts and the write-ups associated with these some of the most useful for my own work, but none of the environments were fully open sourced, and even if they were, they'd be way too slow to use in academic research anyways. So these all fit into that bucket. OpenAI 5 on Dota, DeepMind's AlphaStar on StarCraft 2, emergent tool use or hide and seek, and capture the flag. Now, there was one environment very early on that I want to highlight because it's a good example of what you can get out of building more complex environments. This is M-Agent. It simulates a whole bunch of agents on these relatively simple tasks like this battle, where you have all these locally coordinated agents roaming around. Looks kind of like two schools of fish. So what does it take to learn this type of behavior? If you were a researcher back in 2017, you'd almost certainly think that it would take really specialized algorithms. You'd really have to concentrate on what does it take to learn multi-agent specific dynamics. But it turns out that the same methods that are used on Atari just work here as well. Now, you wouldn't have known that without having an environment that actually requires local cooperation. And that sort of line of reasoning of solving problems simply by having an environment that can answer the question is going to be a line throughout all of my work. So I'm going to start by talking about what went into building Neural MMO, as well as some of the things that I discovered along the way. This is the first recognizable version. I built this in undergrad. The ones before kind of don't count. And I continued building this out at OpenAI. There were a lot of systems in here that only really came to fruition much, much later in the Neural MMO project, and we'll talk about why that is. This is the first public manuscript. It was published in 2019. Notably, that date is before the start of my PhD, but this work does make it into a later 2021 publication that is officially part of my PhD. It's going to be better to cover stuff chronologically here because, one, the environment only gets more complex, but also there's this trend where a lot happens on the environment very early on, then it looks like not very much happens, and then a lot happens again. It's very easy to build an interesting looking simulator. It's very hard to, under the constraints of making it useful for AI research, to continue adding complexity. And that gap in the middle is developing general purpose methods to help with that in the future and with Neural MMO. So this early version of Neural MMO took a little bit of inspiration from artificial life as well. There were foraging and combat mechanics where agents would have to gather food, these sort of darker green tiles at the top. Once they ate the food tile would decay and you'd get this scrub tile, and the food would regenerate, but it would only grow back slowly over time. And then there was water, which they could drink to refill those bars at the top: food, water, and health. They ran out of food or water, they start starving, dehydrating, they lose health, and they can also fight with each other in a couple different combat styles, and that'll take down their health as well. This is what the first released render looked like. You have a bunch of agents wandering around this environment, fighting with each other. You can see some attacks going off, and foraging for various different types of resources, and learning how to explore the map. This was one of the early maps that I used for the early experiments that motivated me to continue on with this project. So a couple points here. That ring at the top, that ring of food, is where the agents would be added into the map. And you can see that big obstacle that goes through the map. They can't walk through that. You can also see the darker green food all over the map, as well as water. So the first really compelling experiment that I saw was that if you just trained agents to survive in this setting, the more agents you put into the environment, the more they just happen to explore. With one agent, it doesn't really explore much at all, it just stays around that spawn region. With 8 agents, you get a little bit of exploration up to the north. With 32, you start to get some substantial coverage. And then with 128, you really get this pretty good coverage of the map, even though you didn't explicitly train them for that. So if you think about this completely removed from reinforcement learning, this is quite obvious, because the environment has a carrying capacity. There's only so much food, and the other agents may or may not be friendly. So of course you have to go farther and farther away to find food and avoid competition. But to think about it that way, you really have to ignore the context of how reinforcement learning was seen at the time. Multi-agent learning specifically was this really hard problem that really you needed to push on the algorithm side. And this would be considered a way too complicated environment back then for most small-scale research. You know, you had these small environments that would have 2 agents, 4 agents. You could solve them in a few time steps. And the goal was to really understand the dynamics from that. The way to make progress was not to make a very complicated environment, throw a whole bunch of agents into it with a general objective, put the simplest possible learning method on that possible. This was vanilla policy gradients, and then expect something to happen. But this is precisely what happened. And by continuing to make the problem harder from conventional wisdom, we continue to get more interesting results. So in that first experiment, we had all of the agents controlled by the same shared set of neural network weights. That does not mean that they're the same agent, they're controlled independently, but if you were to put 2 agents in roughly the same circumstances, they do the same thing on average. Well, in this experiment, we instead had 8 different sets of neural network weights. You can think of that as 8 different populations of agents or 8 different species, where each set of weights is controlling a subset of the agents. And under the exact same experimental settings, the different populations separate to different proportions of the map. You see this yellow population at the top left, this green one at the top, blue down to the right, cyan. And then actually, coming around to this left side of the map, we get the yellow and some of the red population. And this was interesting because we never saw this happen in any of the other experiments. This was a pattern of exploration that simply didn't come out of the other ones. So maybe there was even some applicability to getting better learning using a method like this. There were a couple of other experiments that generally followed this pattern of going against conventional wisdom and giving interesting results. I'm going to skip a few of those here, but in that first release, I had some tools for procedurally or manually generating maps. I had baselines for simulating agent lifetimes and training using policy gradients, as well as some visualization tools I'll talk about in a bit. It was still very hard to do any work in this area because most of the reinforcement learning tools were not designed for this setting, but it got a little bit easier. The next bit of work is from the first year of my PhD proper. I had a couple of short form papers and one longer archive manuscript that covered the first few updates to Neural MMO. Various authorships on these, but for the most part, it was myself, advised by Phillip, Igor, who advised at OpenAI, and Yelin, who helped with some of the very early experiments. I started by giving Neural MMO a new coat of paint to support additional features going forward. And I added these different skill systems where if you click on an agent here, you'll be able to see the various different skills it possesses and their levels. So there are various skills related to combat, various skills related to foraging for food and water, fishing and hunting up there. And as agents fight, they get better at fighting. They inflict more damage, they can take more hits and so on. And as they gather food, they're able to gather and store more food. So the dynamics at the start of the game become not the dynamics at the end of the game. And you have to take into account what other agents are doing so that you don't end up in a disadvantageous position later on. Right, there are two of these slides. There's nothing on this slide. One of two places where I just want to talk about something, because this is the first major problem that I encountered with Neural MMO. The project is modeled off of games. There's a standard playbook for writing games. I could write a pretty interesting MMO light in a year, no problem. But it's not just a game, it's also an AI simulation, and there are additional constraints from that. This thing needs to be fast, and that means that we're not going to render this during training time, which means that we need to train on local state data. But as the environment gets more complex and interesting, which is something that we want, at the same time, that state data tends to get more structured and complex as well, which makes it harder to put into a neural network to actually train anything on. So getting that balance right was the first real difficulty with this project. This is the architecture I came up with. There are going to be a couple of high-level takeaways from this. So the first is going to be the representation that was used for the inputs. Up there at the top, everything is going to be represented as a set of entities. So anything that you can see in the environment, a tile, another agent, is an entity. Each entity is represented as a set of attributes. So for an agent, it's health, it's food, it's water, any observable properties. This network is going to take in all the attributes of all the entities. It's going to embed all of those attributes to fixed length vectors. And then we're going to apply two layers of squashing. So we're going to squash all the attributes of each entity to get a vector representation of every agent, every tile. And then we're going to squash all of those again to get a vector representation of the observation as a whole. Now I say squash, this can be a sum, this can be an element-wise max, but in general, this can be any attentional function. This can have learnable parameters as well. And then this observation is going to go into a standard network like an LSTM, and we'll be ready to decode actions. Some actions are very simple to decode. Moving up, down, left, right, you just add a layer that is from the hidden dimension to 4, or however many action choices there are. But we want to support a little bit more complexity in that as well. Let's say that you want to target an agent with an attack. It'd be nice to be able to select the agent from the input directly. So in order to do that, you need something like a pointer network, which takes the entity embeddings corresponding to the agents that you can see and then dot products them with the hidden state. So this gives you a distribution directly over the agents that you can see, and this lets you select candidate targets. Conveniently, and part of the design, we've already computed those up there. So we can do this type of action for free using this network architecture. The key takeaways from this, 2 layers of observations as opposed to 1 or arbitrarily many. It strikes a good balance between letting you design complicated environments, but also letting you have a relatively simple architecture. And then this also gives you a little bit more freedom on how to specify actions as well. This high-level design was good enough for the whole next 5 years of Neural MMO. There were some modifications, but never deviating from this design. Quick demo of current capabilities on 1.4. You have a couple of agents here fighting each other, and we're going to see what happens when you have a train policy. I added this little flash animation to the attack so you can see when agents are fighting. But you can see that generally these agents are spreading out. They are exploring the map. And you can see a few in the center. You can see the levels to the left of their name as well. So I wanted to give researchers better ways to understand what was going on. So I added these overlays where you can see where all the agents have been directly within the visualizer. But you can also reach into the policy and look at, say, the value function to see how agents are viewing their local environment. There's also a smooth version that gives you a very good picture of what it is that agents have learned. If you look at the individual agents as well, that's another sanity check to see if they're doing something interesting, fighting, gathering food, gathering water. And then, since this is an environment that has some complexity to it, it's useful to compare to random policies. Random policies are very adept at jumping into lava or starving, not much else. And then, just to be a little bit pedantic here, you can go look at the individual agents, see that they have food right over there, but they won't go and get it. And you can also see that if you look at the overlays, even if you let this thing run for quite a while, they don't really explore, and the value function looks pretty random as well. Neural MMO was first formally published in 2021. NeurIPS decided to introduce finally this datasets and benchmarks track that actually had environments as in scope. So once we had some publication on this, we started getting some users, which sped up the project as well. This included all the results I just talked about and a few new ones. The main new feature of this version was NPCs. You have these scripted agents at the top in orange and in green. They will fight you if you try to attack them. And if you defeat them, you can get armor. So that'll add some complexity in a bit. The other new feature was just scale. We made the maps be able to be way larger, did some engineering around that. It would take 10 minutes to walk across those, and you could have up to 1,024 agents per map. The addition of NPCs almost immediately gave us this interesting finding over the course of training. I just started logging the acquisition of equipment and defeating other players and exploring the map as different metrics. And over the course of training, you get this very clean phase shift, where first, agents learn how to explore on the left in purple and various colors. Then they learn how to fight each other. And then as you train for much longer, they learn how to defeat NPCs to gather equipment. So you get these various stages of learning just by having the additional complexity in the environment. I replicated the more agents equals more exploration result on larger maps. This is with 4, 32, and 256 agents. And I even got this result to hold at least a little bit on the much larger versions of the maps. This is several hundred tiles of exploration. Doesn't really work on both sides, but this was pushing the limits of what the infrastructure could handle at the time. This is the second and only other place that I just want to talk about something, because what I consider one of the more important contributions of that paper got one sentence in the actual manuscript. This whole thing ran 50 to 100 times faster than previous versions of Neural MMO. And this wasn't by rewriting it in C++. This wasn't about adding a whole bunch of new complexity. What was going on here was, if you remember that talk about having to take structured data and put it into neural networks, you also have to be able to take structured data out of the environment in the first place. And if you write Neural MMO or any simulator like you'd write anything else, all that data is going to be scattered all around memory. This is written in Python to make it easy and hackable for researchers. That's all very slow. So the solution to this was to just take all of the data that was associated with observations and stick it in a big tensor somewhere. Now to compute observations, you just have to slice into that tensor with some fancy indexing. And if you think that this is going to make the environment harder to continue developing, because now you have to manage this extra memory, well, with a little bit of syntactic sugar, you can make it so that, let's say, whenever you have to update the player's health, then that update will be mirrored into the data store as well. So you can just ignore that this change even occurred. This gives you 50 to 100 times faster computation of observations, which was the key bottleneck step in everything. Once I figured this out, this let me continue scaling the project. The next update was only published as a short format in the iClear workshop, and it didn't even contain any neural networks. But this is my favorite paper. It added a huge amount of complexity to the environment. There were 5 new professions. each associated with a new resource. You could level up these various different professions. And there was a whole new item system where you could get armor, weapons, equipment, tools, and consumables. And all these various items, which were all linked to the different professions, could be traded on a global market. So agents could create their own dynamic economy.
Wow.
It took a while before we could train neural networks to do this in practice. So in the meantime, I made some scripted agents. And they had this basic heuristic search for pathing towards nearby resources. And they had these, these heuristics as well for deciding whether it was safe to engage in combat, whether they should buy or sell items, and so on. And I ran 2 experiments based off of these. In one, I gave all the agents the same script. And in the other one, I set the script for each agent to only care about a specific profession. So instead of searching for all nearby resources, you just care about one resource. Or instead of all of the different combat styles, you're just going to fight with melee, for instance. And if you set it up this way, you have this population of generalists and this population of specialists. And the specialists do better than the generalists across just about every metric. They get higher levels in their skills, more experience, they get higher quality tools and weapons, and they get much more equipment as well. So this doesn't show you that neural networks can learn to do this in Neural MMO, but it does show you that the simulator has the complexity to replicate an important incentive structure from the real world, the incentive to specialize. The next and final core environment paper was presented at NeurIPS 2023 with a whole bunch of collaborators. This was a big paper because this was the release of Neural MMO 2.0. It was a full rewrite of the environment, making the base simulation 3 times faster, the training of baselines 10 times faster, and it added a key new feature as well, which was a task system that would allow researchers to specify what their agent should accomplish in arbitrary code. This new task system was heavily inspired by the DeepMind XLand paper, in which the authors had this environment. If you're familiar with the old Clever VQA dataset, it's an RL environment version of that. If not, it has various different shapes of different colors, and then you can write predicates over those shapes, like purple sphere near black pyramid. You can and or knot them together with simple relations. And then if the agent makes the statement true, it's completed the task. So it can move the objects around, move the objects next to each other to make this statement true. In Neural MMO, I wanted to do something similar with way more agents, deep access to Neural MMO's rich state to let you write more expressive tasks. And I didn't want to have a physical simulation or rendering during training so that it would stay fast in academia. I had to design 2 APIs to do this. The first is substantially similar to the DeepMind XLand one, except it's arbitrary code instead of a domain-specific language. In this task up here, all members within range, we want to check if a group of agents are close to each other. We provide you with 2 wrapper objects to help with this. GS, which is the wrapper into the game state that lets you look at all the variables in Neural MMO. And then conveniently, we also give you this subject object, which gives you vectorized access to the data in a group of agents. So in this case, you can look at subject.row, subject.call, get the positions of all the agents, compute a distance metric, and then you can return whether the task is completed or not. We also made the completion criterion continuous so that you could provide rewards for a partial completion as well, which is useful for curriculum learning research. The second API was needed because Neural MMO is a bit more complex as a simulator. The top one would let you write any condition you want over game state, but let's say that you want to ask if an agent has consumed an item. Has the item before, item is gone afterwards, but maybe it sold it or got rid of it in another way. So you need to also be able to track changes across state and disambiguate when there are multiple possible reasons. To do that, we added a event API that allows you to track these sorts of changes. We coded in all the common events you would care about, and you can add your own as well. So with that, 3 lines of code to write all possible variants of consume a specific type of item of a specific level and a specific number of these different items as well. The space of tasks is arbitrary code. That's difficult to put into neural networks unless you use an LLM. So we embed the source code, including the doc strings of all of the tasks that we wrote. And this is a nice use of LLMs with RL because we never have to run the LLM during training. We just pre-compute the embeddings for all the tasks. We can give those embeddings to agents whenever we want to specify a task, and we never have to run that LLM again. We also get this nice embedding space of tasks as a result. So here we have various different tasks associated with leveling up skills, acquiring and equipping items, drinking water and consuming other things, and as well as buying and selling things as well. You'll get the demo of 2.0 at the end. First, I want to talk about the other side of my work, which is competitions. To date, we've run 3 competitions at major conferences, 1 at ICML, 2 at NeurIPS, that have totaled 3,500 or so submissions from 1,200 participants. The first major one was at ICML 2022. This was on Neural MMO 1.5, which is the version before I introduced trade and all the new professions. We instructed participants to train a team of 8 agents to complete objectives, and they'd be evaluated on maps they'd never seen before and against 15 other teams that submitted agents that they had not been trained against. This version of the environment didn't have the task system yet, but I did try to make the actual objective somewhat multimodal. I had it be defeating other agents, defeating NPCs to gain equipment, so acquiring equipment, exploring the map, and foraging for resources. So there are 4 categories. Each category had 3 different difficulty tiers, and you could score points by completing any of these. And only 1 agent on your team had to complete a task for you to get full credit, so you could have different agents on your team assigned to different tasks as well. A little bit of the organization here. We gave participants a starter kit that had the baseline policy, training code, and also the copy of the environment itself, of course. Participants would do whatever they want, train their policies, and then submit them to us. And we would evaluate their agents first against copies of the public baseline that they had access to. If they did well against that, they'd be evaluated against much stronger versions of the baseline that were kept private for the duration of the competition, just larger versions that were trained with more compute. If they passed a certain threshold as well, they would be put into the submission pool, which is the PvP track, as we call it, player versus player, against all of the other submitted policies. And at the end, we took the top 16, we ran 1,000 games, and we saw which agent won the most number of games. The architecture used by our baseline was conceptually almost identical to the architecture I described before. All the stuff on the right is the same, that's just an action decoder. Stuff in the middle is an LSTM, and then the stuff on the left is various types of encoders for different types of data. So instead of just having linear layers or sums to encode all the different entities, you can do a bit better if you use convolutions for 2D map data, max pooling for agents, and such like that. But conceptually identical. In this competition, we received and analyzed over 1,600 submitted policies. We did allow scripting as well, so we got a bunch of scripted submissions in there. And scripting did very well for the first 3 quarters of the competition. But by the end, reinforcement learning had won out. All the top submissions were rather different as well. Some of them were relatively better at exploring, some of them were relatively much more aggressive, and the winning policy was very focused on farming NPCs for equipment. Oh, and it gets even funnier. Wait until you see that. But first, agents spawn at the bottom here. Here are a couple different policies. They act differently if you just look at where they go in the map. This one goes in circles all the way around to get the exploration reward, has a bunch of other agents around there. This one kind of explores a little bit, but it doesn't go all the way around the sides. It meets up in the center a bit and explores out from there. There are more of these as well. This one was rather interesting. Doubles, literally cuts around the corners and then meets in the center. And then the winner, passerby, plays pretty close together as a team for a while. And then once it gets to the middle, it splits up and explores from there. This is not just an artifact of cherry picking one trial, by the way. If you look at the heat maps over 1,000 games, they all spend their time in different places on average. Let's take a look at some replays. So this video is provided by our partners at Parametrics, who helped with organization and evaluation, as well as promotion. We're going to zoom in just a moment here and take a look at some specific agents. Here we can see the passerby model farming agents for equipment. There are a couple different There are a couple different agents that did this. Here we see this, somebody would close that door, please. Here we see agents that are spawned at the corner of the map. They're engaging in some initial aggressive combat. It's pretty difficult to avoid getting into a fight if you happen to get the corner spawn. We randomize this across games though. Some agents are very aggressive even when they don't have to be early on. So here, this team takes most of their agents and pushes them to one side to try to surprise this other team. They gain a numbers advantage, and this is a fairly effective, if risky, strategy. Did not win first place. You'll see that they do end up defeating more agents than they lose in this. Passerby was much more conservative. It would only ever commit 1 or 2 agents to the initial fights, and then the rest of the agents would get on over to the center of the map and start farming over there. Okay, so this is the NPC farming behavior, but it was more effective than it should have been because of a bug. The attack range for NPCs was computed differently from the attack range of agents. So if you hit it in a diagonal like that, they couldn't hit you back. This ended up making the competition more rather than less interesting, but it did let agents get power farm for lots of high-level loot. A couple of coordination failures that you'll see improved upon in the next competition. If that other agent had been just a few seconds earlier, it would have been able to avoid that. Here's one where these agents should have both fled or both committed to the fight instead of this. Bye-bye. And there was some good coordination. So here, it's caught on the corner of both attack ranges. It doesn't have any room to move out of there. That's enough examples for this competition. The second competition was hosted on the version of Neural MMO with Specialization and Trade at NeurIPS 2022. We resolved a few of the difficulties we'd had at ICHKAI. We made the PvE only 2 stages instead of 3. We ran more evaluations for PvP. We made it a little bit easier to get into the PvP submission pool. One other big change, since the environment was way more complicated in this version, I didn't want to write some weird objective that was a combination of getting equipment and leveling specific skills and defeating opponents. So what we did instead is we took a page from Battle Royales and I added this death fog mechanic that pushes agents to the center of the map over the course of the game. So they're forced to fight, and as a result of that, we can just make the objective survive and defeat other agents. And then all the new items and skills just help them to accomplish that purpose, since they can't win by running and hiding. Baseline was almost identical to the previous one. We added encoders for the new item and market systems. We added buy, sell, and use actions for the new actions. These use the pointer action structure of the, that was designed 4 or 5 years before this. The winning policy was structurally very similar. All the stuff on the left is various specialized encoders. The top right is a virtually identical action decoder. The main innovation was this module in the middle, where the submitter had a transformer that applied over the embeddings of agents. And by doing this, their agent was able to learn much better cooperation among the team, and much better awareness of what other agents are doing. This time, RL far outperformed rule-based systems, scripted agents, but all the top agents used at least a little bit of scripting to help macro over the complicated market actions. We also had an imitation learning track, but since the RL policies did so much better, the quality of the data became too low by the end of the competition for it to do very well. Let's take a look at some of the replays, focusing on coordination specifically. So this is a little bit small in this video, but there's a Relikun agent, which is a winning agent in green, and there's a red agent there, and they're getting into a 1v1 fight. But if you see at the top, there's some additional Relikun agents that are coming over to help, and watch how quickly they come to help their teammate. Here, they perfectly encircle and trap this agent. So it is stuck there, and they quickly eliminate it. One other thing that I should mention about both Neural MMO in this case and the Battle Royales that it was, they're very gratuitous with their animations. They're fun. But hold on. I'd like to pause this for just a moment, because one thing that you need to be aware with games of this kind of type and genre, it's good to play with your team spread out a little bit, because you can get more resources from a larger area. But as soon as a fight starts, you have to get there fast, and that requires coordination. Watch how well Rallycoon does at this. You're going to see that they're about to get ambushed by a few passerby agents, but watch how quickly they turn the tables. Let's try that again. Here? Yeah. So watch how quickly they turn the tables. All the Rallycoon agents are going to collapse. They circle in from behind. And very quickly, now it's an even fight, 3v3. And now they are outnumbered. And they don't lose a single agent despite this, this pretty bad ambush that they were subjected to. It's not all PvP. Here's an instance where there's a high-level NPC that requires many agents to help defeat. We fixed the bug by this competition. So here are the 3 agents on this team cooperating to take down this high-level NPC and get the high-level equipment that it drops. This brings us to the most recent and final competition, which was hosted on Neural MMO 2.0. It was not team-based, it was task conditional. So you train 8 agents independently, not as a team, and we give you tasks to complete at evaluation time that are going to be very similar to the ones that are seen during training time, but not identical. As part of the baselines, we generated and embedded all possible simple variants of tasks you could think of. So fighting with a specific combat style, scoring a certain number of hits. We had things like buying, selling, and equipping every type of item in the game, acquiring amounts of money, exploring the map, leveling up skills, so on and so forth. So all the different types of primitive tasks we gave participants as embeddings. This is where I am out of fancy figures because this competition just finished. In fact, we were getting new results in for this as recently as 24 hours ago. However, I do have a nice demo from the evaluation that I want to preface with a few statistics. So in this competition, agents were trained with CleanRL in 8 hours on 1 GPU. All previous competitions, and pretty much any fancy environment that you look at, requires much heavier learning frameworks, TorchBeast, RLlib, and the like, and 1,000+ lines of dedicated infrastructure to make the framework that's not designed for that handle that environment complexity. So in the most complicated version of Neural MMO, we were able to have the fastest training baselines on the simplest infrastructure. So it became a lot easier to do research in this space. And under these constraints, the top participants were able to achieve a 4 times improvement in number of tasks completed over our baseline. There were 2 co-winners with virtually identical performance. And I'm going to risk a live demo. This is on the Neural MMO 2.0 website. So you can just click here to demo. There's a built-in file that's somewhat old. We will release this new file shortly with the proceedings of this competition. It'll take just a few seconds to load. And then we get this nice client that shows us the environment. We zoom out a little bit here. You can see the size of the map. We'll start this. You can see all the agents spawn in, not in teams, since this is not team-based. And you can click on the individual agents to get some information on them. There's one in particular that is fun to watch. We're going to watch this one right here in green. And you can watch it level up various different skills over the course of this game, acquire different items, and generally explore the map. So I'm going to put this on 4 times speed. And we can watch this. Very quickly, it's going to acquire a little bit of armor and a few tools, some consumables. It's going to equip the armor. You'll see that it has this very spammy equip and unequip action that it does. On one hand, this is kind of like how Pong RL agents will win by doing this very spazzy, not human style of play. But on the other, this actually lets you not have to remember which items you haven't equipped yet, because equipping items is one of the common tasks. So it usually keeps the armor on to maintain its defenses at the least, and spams most of the other things more often. It quickly, all the items you see disappearing for the most part, it's selling on the market since they're tasks for selling stuff, and also it can get some money. It will buy things occasionally as well. You can see in that level panel, different skills are increasing. Hasn't done any combat yet. This was a much more passive competition since why get into dangerous combat when you can, at the very least before that, go accomplish all the other foraging-based tasks. So agents play a little bit more conservatively. This fog animation you see creeping in, you can ignore that. We didn't have time to remove that from the previous competition. They are perfectly fine standing there. And while I've been talking here, this agent has leveled up at least once all of its different foraging-related skills. It just got into a little bit of a fight there. You can see it leveled up its range skill, one of its combat abilities. We're close to halfway through this game at this point. You can see that this specific policy has 7 of its agents still alive. 111, which is the one that we're looking at, is the one that's exploring the farthest into the map right here. The resources that you see disappearing, that's it gathering resources. It's getting the items from those. Each resource associated with a different profession will level up the skill after it collects a certain number of them. These two are not particularly friendly, so they will hit each other a couple of times if they get too close to each other, but they tend to play chicken and not really commit to anything. Halfway through, I will speed this up just so that we can see the aggregate behavior in the end state. So meanders around, gets a little bit of experience hitting some of these low-level NPCs. Plays pretty safe, doesn't do much, but generally you can see that it's explored a decent chunk of this, this map, all over looking for different resources. It's gotten fairly far towards the center. It's always had the set of armor on. You can see it's leveled up all of its various different skills quite a bit at this point, outside of the combat ones. In this particular case, this agent hasn't decided to do too much combat. And okay, this brings us to the end of the simulation. There are 2 other things we're gonna do here before we wrap up. We're gonna click a couple of these other agents to see how they did. This one also has a full set of armor, different skills. Sometimes if they get into combat very early on, they get some levels, so they become more comfortable fighting. Here's another one, full set of armor, and there's another policy in here as well that has a few agents still alive. Plays a little bit differently as well. I'm gonna cheat. I can't see from back here. Okay. So a little bit different, this one. Doesn't have this high level skills, but I actually think it does a little better with its item management. These are all rations, which the agent can consume to restore health in a pinch. The other agent probably shouldn't be selling those constantly. It should probably keep a few of those for a rainy day. And the other agent is fairly similar, has some rations as well. So the last thing I want to show on this demo is the market state. So we can see, if we scroll back to when there are more agents alive, we can see them buying and selling stuff with each other. Various different things are for sale. Agents will list items, agents will buy items. You get this little bit of a dynamic economy in here as well. Some conclusions from all this. First, I want to just conclude the story of Neural MMO here. This was a really early render. It was somewhat derivative, kind of Minecraft-y. But I was already thinking about how do we get more complex and interesting data for reinforcement learning. And this version was from July 8th of 2017. I actually managed to get it to build as well. Back then, this project was nuts to anybody I described this to, including to some extent Phillip. But if we actually go forward less than 2 weeks, this is when PPO is published. And with the benefit of hindsight, we now know that today, PPO has been tremendously effective on a huge range of problems. But there was so much focus on trying to improve over PPO and relatively so little focus on trying to get better environments. So in hindsight, it seems rather reasonable to spend more time on the environments. And I think that even today, there's been an underinvestment in those, and hopefully my work can help with that. Some of the concrete conclusions on how that will happen. With Neural MMO, we've taken the line in the sand where we know what PPO can do at small scale on hard problems, and we've jumped it ahead quite a bit. So all the things that you see in PPO, all those skills, all this in Neural MMO, all those skills are learnable at small scale with PPO. In order to make that happen, really the only barrier is this huge gap in simulation engineering, where you have to get those details right to have the environment run fast enough. So Neural MMO gives you an environment where those details have been worked out, but it also gives you something of a playbook for building more simulations in the future because you can reuse those same design decisions. I'd like to thank my collaborators over the years, especially in Neural MMO 2.0. This was just such a massive undertaking as a project. I'd like to give Kyung in particular a huge shout out for really helping us to make this possible. I'd like to, of course, thank Phillip for letting me do all of this crazy stuff for the last 5 years. And above all, I'd like to thank my family. They've supported me this whole way. I wouldn't have been able to do it without them. They're here with us. So thank you. This is for you.
Okay, excellent. Thank you, Joseph. So now, yeah, let's do that. So yeah, now we have some time for questions from the audience, and I'll check on Zoom as well if you want to ask a question on Zoom.
Yeah. We'll do the Zoom ones via text, except for Eugene's, and we'll prioritize the in-person ones. But I'll take some.
Yeah, let's start with in person.
So have you investigated using this kind of framework for stuff like robotic transformers, where you give them sort of like complex joints and then sort of a much more complex articulatable environmental sandboxes, and then kind of letting the agents roam and kind of like.
So my work is very much in a different direction in that I focus on high-level complexity. Getting the low-level details right is very important, but it's quite different. So in my mind, I want to push the complexity of the types of reasoning challenges that agents can accomplish and actually abstract away those details as much as possible so that we can be training on hundreds of years worth of simulated data rather than the much lower amount of data we typically have in robotics. If you had $7 trillion, you might be able to get that level of data in the robotic space, but I don't have that yet.
Yes. So what's in the future for Neural MMO? What's the next step in the project?
Currently unannounced. I do have some ideas, and I do think that the things that you see here, this exact same level of complexity, could be achieved at least 100, if not 1,000 times faster. Not in Python, not in pure Python for sure, but with some slightly different design considerations, I think it could be done. I'll take a crack at it at some point.
I'm curious if you saw sort of like any interesting emergent behavior in like the economy, like what ended up being like the market price of like refillable versus like another piece of equipment.
Refillable, yeah. I mean, I wish we'd done more in that space. Frankly, I wish I'd like taken the current policies and thrown them on that early experiment where we did it with scripted agents to see if we could do the same thing. But the competitions really had to take precedence over that once those started taking off. So, I mean, we are seeing agents buying and selling items on that, but we're not seeing like the nice price fluctuation graphs as much as we want. Though we did have a little bit of that in the NeurIPS 2022 paper. So if you look at that, there are a couple price over time graphs.
Have you ever seen any like collaboration between groups?
So that is banned in the competitions. It's battle royale rules, so you're not allowed to cooperate outside of your team. This is one of the things that I wanted to have more collaborators using Neural MMO for other purposes, because between building the environment and running the competitions, I was at capacity doing that. So my hope is that we have this research platform now. We have a couple people using it for different things, and we'll see more efforts on that type of a thing. Actually, Kyung has some mini games that he'll be sure to talk about in the next few months.
You talked about like state representation being important for making the simulator run fast because you didn't want to do rendering. But I wonder, like from the standpoint of learning, like how do you balance having a state representation that's useful for like running simulation where you have this big tensor of like items versus like a representation, like an image-based representation where the agent can extract the useful information, and how do you balance those things?
So the way I think about this is that exactly or almost you can take the data from the local state observation, and you can use it to produce the render. So in some sense, they're equivalent, and I'm just cutting out 100x overhead. If you had a really fast rendering library, maybe you could provide a reasonable pixel option, but I haven't seen any case where it's like less than a 10x overhead, and that's being generous.
You've been pretty passionate that like you don't really need that many algorithmic changes and that PPO can take you very, very far. Are there any things that you want to build in MMO or that you have built like the later stages in the economy, like the level 10 items and stuff, that you think that there's just no way that current algorithms like PPO can solve them?
I think it's likely that we're going to hit that at some point, but I haven't seen it yet. So I started building Neural MMO in part looking for places where current algorithms would fail, and they just never did.
Have you thought about transferring the complex behaviors learning in your MMO to other environments or games or tasks?
Oh man, I've been asked this so many times and I've always said it's a bad idea. And here's why. You can do transfer learning, it works. We've seen this in some larger scale DeepMind papers recently, but you need to have a much wider training distribution and a much more complicated environment before you can then transfer to something that is much simpler. So when you're trying to like transfer from one thing of one complexity to another thing of this comparable complexity, I kind of think about it like trying to transfer from one class on ImageNet to another without seeing that training data, when you only have like 5 classes to begin with.
Sorry, would you think it will become easier once you add more and more complexity to your MMO?
Yes, eventually, but it would have to be, you'd have to be at or above the complexity of a full MMO. I mean, my subjective hierarchy in my head is that a full MMO, complexity-wise, is probably about the same gap as from Atari to Dota. That's how I have it in my head. There's another one of those at least to the real world, but that takes us several orders of magnitude.
So we have 1 or 2 questions on Zoom.
Let me take a look.
Yeah, I can read them. What are your favorite funny strategies that you've seen over different runs?
Oh man, all the funny strategies end up being frustrating because they take 2 weeks to find. I think the power farming one was pretty good. It was literally that I had an L1 distance on the attack range of the NPCs and an L infinity distance on the players. So they learned that you could hit on the diagonal. And that would have been fine, except in that build of Neural MMO, there was an attack that would freeze you in place. So they could freeze their target in place at a diagonal, and that attack barely did any damage either. But they would just spam it for like 100 steps, and then they defeat the highest level NPCs using it. It's hard to beat that one.
Okay, and then I think this is related, but are you optimistic about the creativity you see expressed in the learned behavior?
Yeah, I mean, the cooperation I think that we saw in the NeurIPS 2022 competition was pretty compelling. I'd like to see that same thing in these competitions. It's a pure infrastructure limitation. It's really hard to do learning with variable team sizes. So when agents die and the team size gets to be variable, that messes up learning algorithms badly. And it's not like a mathematical mess up, it's just like it messes up the batch sizes problem and it destabilizes training. So if we could figure out how to fix that, then I think you'd probably be able to get cooperation, like cooperation with all the new mechanics at reasonably small scale. And then after that, you need more game mechanics.
Well, okay. Maybe I'll do this one as the last one. What are the best ways to contribute or get involved in the project?
I wish I'd paid for the vanity URL at this point, but on the website, neuralmmo.github.io, there is a Discord link, like a 1,000-person Discord that's built up slowly over the years. I'm not difficult to get a hold of there, and we definitely appreciate open source contributions.
Cool. Any last questions from the live audience? Okay, I think with that, there's one over here, yeah.
So why do you consider Minecraft to be a bad environment?
Okay, there are 2 reasons. One, it's really, really slow, like unbearably slow. And The other one, and I don't consider it bad for all AI, it's for tabula rasa RL specifically, because there's no incentive in that game to build giant castles and do all the stuff that people find interesting. So the incentive structure needs to be contained within the game if your objective is good tabula rasa RL. So my favorite like single agent high complexity environment that already exists off the shelf is NetHack.
Okay, cool. So I think with that, we can thank Joseph, and we'll do the